Hello. I wanted to present you the second part of our training, REPTiS training webinar. Now the focus is on the beneficiation opportunities of ilmenite-bearing heavy mineral sands, including inside our REPTiS project. I will start directly. Maybe if you can. Yeah, a short introduction from my side. My name is MIchael Lechner. I am working at Montanuniversität Leoben, started with my bachelor's in 2018, gone with a master's, and now since September 2024, I'm writing my PhD thesis at the chair of mineral processing. The topic here is the beneficiation of Ukrainian ilmenite heavy sands to build up a contribution to improve Europe's self-supply with critical raw materials from its own deposits. At first, I will start and give a short overview about the topics. First one is the basics in mineral processing. What is the definition, the main questions in mineral processing, and our approach at MOL. Second is the mineral processing on the example of our beneficiation plant in Ukraine. Third one will be bridging with downstream processing, the bridging between mineral processing and metallurgy, and in the end some unexpected insights from our work with the material from our deposit in Ukraine. So at first, what is the definition of mineral processing? It is basically the treatment of, on the one side, primary raw materials, and also on the other side, the treatment of secondary residues. This can be slags, dusts, and so on, with the main aim to produce a raw material concentrate or raw material product with market reliable properties, using physical, physiochemical, as well as chemical processes. The overall objective is to maximize the value and build up a fixed feedstock for downstream processing. What are the three main questions in mineral processing? First, it starts with the mineral content. That means which mineral phases content are presented in our samples. Second one, how strongly are the intergrowth or liberation conditions? Are they liberated? Are they good liberated or not that good? And third one, the characteristics. So which properties can be used to separate different mineral phases from each other? These three main questions, more or less the answers to them, give us an in-depth raw material characterization and gives us the opportunities to separate different mineral phases from each other. It can be seen in a graphical way, something like this. We start with an ore from mining site. Through mineral processing, we produce concentrates, or when we look at the sand grabber industry size classes, and in the end, we make it ready for downstream processing. That can be a product for a concrete industry or for the steel industry, or maybe compounds for fillers or additives. So, raw material characterization, the approach from Leoben. We have more or less our own unique way to approach this characterization. As I mentioned before, it more or less overlaps with the three questions in mineral processing. At first, what is the mineral content? It can be determined on the one side using the chemical composition of a mineral. These insights we get from XRF analysis or slightly chemical analysis in general. And the second one is the crystal lattice structure of a mineral. We obtain this by XRD, microscopy, and so on to get first insights of our raw material. And these both analysis combined gives us a clear insight into the mineral content as well as its distribution. This goes on with our second main part, as it also mentioned before, the intergrowth and liberation conditions. Now, this is a very important topic because generally in mineral processing, we prefer free and simple intergrowth conditions. That means that mostly separated and only has one boundary surface. What's not so preferred, or what is harder to beneficiate, is when our minerals, our mineral phases, are complex intergrown with each other. This makes it even harder to separate them as well as to process them. How can the conditions be determined? On the one side, microscopy, subjective method with stereo microscopy or polarization microscope, and the second one with diffraction class analysis. This is an objective method where we separate an amount of particles into property classes. So we separate particles through its properties. It can be the density, it can be the particle size, or it can be the magnetic susceptibility. In the end, we characterize them into different classes of particles. Example here, we have quartz and PBS. Some grains you may see they are fully white, so that means they are fully quartz. Some grains are fully black, so this is the PBS, and some of them have intergrowth conditions. So we have content of the white quartz as well as a content of the black PBS, and now it's the challenge to bring these intergrowth grains, intergrowth mineral phases out of each other, more or less to separate them. So that's the main idea of mineral processing. And the third one is the fractional class analysis. It is a method that we have more or less mainly used in Leoben. As I mentioned before, the available properties, on the one side particle size, density, susceptibility, as well as the conductivity and the wettability of the mineral surface. And the procedure is more or less the same. It starts with the classification into, as I mentioned already before, the fractional classes, for example, the density classes, take the weight, do analytical stuff to determine the content, and put all of these informations in the end in a so-called balance sheet. It's a tabular representation of the processing success. And also maybe to put it in a graphical form, it's so-called the Henri-Reinhardt chart, to also get an illustration on the intergrowth conditions that are represented in our raw materials. What's the result is basically a quantity distribution, mass, volume, or quantity, which is displayed in a form of a total frequency distribution. So second one, now I will the theoretical basis that we have built up with the last slides to go on with a step-by-step approach on the specific example that we have in our deposit in Ukraine. The initial situation. The sampling is also a crucial point. In the end, it is important that the samples have to be representative. So the samples that you take out of a beneficiation plant should have to represent the whole deposit on its own. So the Leoben way of sampling, we have a mathematical statistical concept based on standard deviations and confidence intervals. I don't want to go too much in detail. In the end, the sample has to be representative. The properties of the sample that have to correspond to those of the entire deposit is already mentioned. And in our case here, for this example, we received 100 kg of ilmenite-bearing heavy mineral sands out of the deposit. So this is the initial situations. We have here a bag of 100 kg of heavy sands. Starting with the three main questions: mineral content, liberation, as well as properties, which can be used for separation. So, first one, before you start anything out of these 3 points, you took the samples and put it under a microscope. So here we have on the left side slightly elongated angular particles, light, more or less shiny, well sorted. It has to be glassy quartz. And on the right side, we have dark grains. As we already know that we have here an ilmenite deposit, it has to be ilmenite. So this is the first insight on your raw material. When you get it, you look at it under the microscope. As I mentioned, first insights, And what we also see is just only by looking at these two pictures, they are well liberated. So the main gangue mineral here are silicates, in our case mostly quartz, and ilmenite is our valuable mineral. And when we see more or less both of each other, they are more or less fully liberated from each other, which is pretty good and makes it easy to process them further to get out ilmenite concentrate. Next one would be a three-stage fractional class analysis, starting with sieving. So we receive this 100 kg and start to obtain a particle size distribution. We have done that three different sampling or 3 different samples to get more or less the particle size distribution of our starting sample. As well, after analysis, we can represent the different particle size classes into absolute mineral contents. So we see here on the x-axis, we have the particle size classes in microns, and on the epsilon axis, we have the percentage from 0 to 100. So it gives us the absolute values inside particle size classes. And what can we see? The main gangue mineral is for sure quartz in the coarser particle size classes, and the finer we get, the more starts the kaolin as well as the montmorillonite starts to occur. And this gives us a basic insight. And also important here is where do we have our ilmenite. So we can see ilmenite starts to occur at around 63-100 microns and tops at in the particle size class 515. So it also gives us first valuable insights. Where is, in which particle size are our valuable heavy minerals contained? The deviation is based on XRD. That may be a problem when you have mineral alteration. In our case here, when you have a weathering deposit, it tends to be not able to detect the ilmenite because due to alteration, it is not possible to it's not possible for the XRD device to analyze ilmenite as ilmenite because of the weathering, it can't be seen as ilmenite. So it's also important to have always an XRF analysis combined with our XRD analysis. Next one would be the second stage, zinc fraud analysis, to bring our particle size classes into density classes. Therefore, we use a mixture of sodium polytungstate solution plus water to receive our heavy liquid. In our case here, we go from 2.5 more or less 2.3 to above about 3.1 grams per cubic centimeters, and we split our particle size classes that you can see here on the right in the middle of the slide, 1,600 to 1,000 microns. So these are the particle size classes in microns. And on the x-axis we have the density for sure, and on the epsilon axis we have the accumulated mass. So what's interesting here, we see that the highest content of heavy minerals, they are detected in the particle size class 515, and the second one in the 710 to 500. You can see that here because we have the green line here and the red line here. So good. After the second step, our density classes will be further treated. Before I forgot, the Reinhardt graph, it's the graphical expressions. If you think at the beginning I said that, it brings us, it is a graphical way to bring our heavy minerals, in our case mostly ilmenite, in relation with our quartz, with our silicates, with our gangue minerals. And as what we already know is that our ilmenite is more or less fully liberated from the silicates, and in a graphical way it can look like this. We have here the different particle size classes in cumulative form on the epsilon axis, and we have the heavy mineral content on the x-axis, and more or less basically the same that we already saw from the density classes before, that in the particle size class 515, the content of heavy mineral tops, and the coarser the particles as well as the finer the particles get, the lower get our heavy mineral content. So this is also basically a good way to see where are my heavy minerals, where are my valuable minerals, and gives us a very good characteristic overview about the raw material. Next one, now the third step is the susceptibility classes. So after sieving and the density classes, we further split our heavy minerals, in our case here because it's most interesting, into susceptibility classes. That's the third layer of this type of characterization, and it's look like something like this. So what can we see here? Is the particle size classes split into susceptibility classes, which gives us also an overview, okay, where are my heavy magnetic minerals in our case we have ilmenite, so it is magnetically, it's not ferromagnetic, but it is paramagnetic, and we see also in the particle size classes, besides of 163 as well as 1000 to 710, the main ilmenite content is right in between, in the middle particle size ranges. And therefore, we have Franz isodynamic separator. Why? Because this is a device that is more or less makes different raw materials comparable with each other. So the Franz isodynamic Scheider has a device independent. It is a device independent form of characterization when we look at the magnetic properties. Good. So how is such called a balance sheet, or more or less what is the what do we get in the end when we do this different steps of characterization? We get a balance sheet. It can be look something like this. So on the left side, we have the particle size class. In our case here, we have the particle size class more than 100 microns. We split them into three different density classes. Higher 3.1, 3.127, as well as lighter than 2.7 grams per cubic centimeters, and splitting these three classes further into susceptibility classes from less magnetic to more magnetic. And in the end, these susceptibility classes will go to analyzation, chemical analyzation, XRF, and we get a distribution of oxide grades for sure. Yeah, that is the main, and there, out of these grades, we can not only focus on the oxides. We can do this with XRD to get the minerals. We can do it also with ACP-MS, for example, to get a closer look, closer insight into rare earth elements where the content is pretty low. But with this method, it is possible to also detect very low amounts of minerals or elements inside mineral samples. What we have here is throughout this whole information, characterization, and so on, in the end, we have to use this to build up, it gives us information about the raw material, and throughout these informations, we can build up a processing scheme, a flow sheet. And for example, here we have a processing scheme for our beneficiation plant in Ukraine. For example, we get the feed starting with a fixed grid to get rid of the extremely coarse particles. Then we deslime it with hydrocyclones, and then we have a vibrating screen, for example. It's 1 millimeters. Why that? Because when we look at only Reinhardt chart, we see, okay, yeah, our ilmenite or our heavy mineral starts occur below 1 millimeter. So each grains more or less above 1 millimeter is basically just gangue minerals and silicates, so they are not interesting for our process, and we can get rid of them right before we do some density separation or magnetic separation. In the end, we get to intermediate concentrate. RIC means rough intermediate concentrate. They're here, the coarser 1.0 millimeters I have, it can be seen as more as an optional way. So the main focus is there should be on the particle size smaller than 1 millimeter, and this will more or less go on magnetic separation or electrostatic separation. We have this to the flow sheet, and we have a special challenge here with this deposit because in case of alteration of ilmenite, due to that alteration, the properties of ilmenite highly start to change. We can see it in the chemism, we can see it in the color, in the luster, in the density, as well as in the magnetic susceptibility. This alteration has a significant influence on how we design our process. And these insights are in that case so interesting because this alteration influences the hydrometallurgical downstream processing. So for mineral processing itself, we are considerate about that, we know about that, but it's the main influence is for the metallurgical processing after the mineral processing. So this has to be keep in mind to build up, not only focusing on your part on mineral processing, but also to keep in mind what comes after my part. In this case, it's the metallurgical downstream processing, where these significant changes in characteristics may have a significant influence in the performing of leaching or so on. So a different harder insight, how can you see this alteration? Just build or split it. We have here ilmenite samples in the particle size class 315 to 250 and split it into different susceptibility magnetic classes. From the left to the right, we see we're starting with black powder and we end up in a lighter brownish powder. This is due to the fact that throughout this alteration processing, as you already might see it on the left side, the ternary phase diagram goes from left to right, from ilmenite to pseudo-rutile, by leaching out the iron. So on the one side, by oxidizing divalent to trivalent iron, as well as losing the iron in general in an ilmenite claim. So this will be followed by the change in Kara, but a change in density as well, but a change in magnetic susceptibility. And here's how are these things linked to each other. Susceptibility and density are correlated with the stage of weathering. We can see it under the SEM ADX as well as the microscope, the mineralogy, and in the end we can calculate that back and maybe build up a connection with primary ilmenite equivalents, and these insights gives us in the end directly before we do some leaching tests, we have this form of alteration, this distribution of alteration in our deposit, how this will be influence our hydrometallurgy related to solubility, reagent consumption, or leaching efficiency in general after our mineral processing. So these are also things that have to be keep in mind and very interesting and definitely have an influence on the processing downstream after the mineral processing. For example, we can see this on the SM8S. We have on the left side titanium, in the middle picture iron, and on the right side the normal picture. And you can see where we get low of iron. In the middle picture you see it in the darker surfaces. We have an enrichment in titanium. This is exactly that what I've told before. by decreasing the iron, because it's get leached out, the titanium content not increased but relatively increased. So you can see it here as an enriched zones for titanium dioxide. Same we can see under the polarization microscope. We have here this alteration starts from the outside in, so we have more or less this shrinking core model. So it starts from the outside. Also, the cracks along ilmenite surfaces have and significantly influence on how fast, not how fast, but the higher the bigger the specific surface, the faster it gets to leach out on the surface. And on the right side we have this yellowish ilmenite grains, and the more it gets weathered, the more it gets in this grayish, bluish color. Now, what are the opportunities in the beneficiation processes, for example, and also bridging with downstream processing? In general, it depends on so much things. At first, which possibilities do I have related to environmental conditions? So, would it make sense to build up a wet processing plant in the desert of Australia? Maybe not, so better use a dry process route. Second one, are there in my country where I'm currently in, or where my beneficiation plant is located, are there some regulations regarding using reagents, maybe in the case of flotation? If yes, then maybe flotation is not the best way to go. They have to consider another processing way. So the location where the beneficiation plant, more or less where the deposit is, has a significant influence on how we build up these processes. Second one is depending on the raw material itself. Is it well liberated? Yes. Is it already fine? So is it fine and also well liberated? So maybe no comminution, as in our case here, is needed. Second one, do we have some enrichment of heavy minerals? Just by looking at the different particle size classes. If yes, we have it in our case here with zircon. In the particle size class smaller 100, we have a pretty high enrichment just throughout the geological issues, and therefore it may be interesting, or it is interesting to build up a classifier step at 100 microns to directly separate the zircon mineral from the other minerals. And next one would be, do we have magnetite as a gangue mineral in our deposit? If yes, maybe a low intensity magnetic separator would be needed. If we don't have magnetite, we would need that low intensity magnetic separator. So what I try to say is, first one is the location, the environmental conditions. Second one is the raw material itself. And the third one is the downstream processing. Do we have hydrometallurgical? Do we have a pyrometallurgical way? Do we maybe have influences through the reagents that we use in flotation? These are all things that we have to consider with and work together with our guys from the metallurgical department to always and directly go hand in hand. Okay, what is the plan after mineral processing, and not, okay, we go to the concentrate and after that it's not interesting for me. That's not the right way. But the way would be, okay, to keep the contact up with the downstream processing and say, okay, the idea is hydrometallurgically, okay, maybe these reagents don't influence, or they will influence the efficiency of leaching, for example. Okay, better I look at something else to replace these reagents. So this always a good idea to keep what is behind and also what is what was before we get the material out of the plant. Good. We have also some unexpected insights, and I also mentioned it with the zirconium in this one tailings fraction after magnetic separation. We have pretty enrichment in phosphates and also in zircon, and they tend to be rare earth elements bearing as well as yttrium bearing, and for sure zirconium is known as hafnium bearing. We come to this insights due to the fractional class analysis, and we see in the particle size class, as I mentioned it before, smaller than 100, we have directly without any processing, just by sieving an enrichment of these two minerals, and this makes it even more interesting to have a detailed look on which rare earth oxides or rare earth elements are contained, in which minerals, how is the grade of the different rare earth oxides inside zircon, inside phosphates. It is definitely xenodium as well as monazite, and how are they how is the distribution in the different mineral phases of the phosphates as well as the zircon. And yeah, as I mentioned, zircon, the light rare earth oxides in zircon as well as xenodium in the sustainability class 1 to 1.4, as well as higher than 1.4, it's miswriting here. And the heavy rare earth oxides plus the yttrium is substituted in the data structure of zircon, and the zircon occurs in the particle size class smaller 100 and in the susceptibility class higher than 1.4, as well as 1.4 to 1.0 amperes. In our case here we have partially magnetic zircon due to iron coatings on the surface. It's also interesting insights. And yeah, so in the end I want to say these are all the insights that we just get out of the characterization of the fractional class analysis, and by adding more time in the characterization at the beginning, you definitely get some deeper and also some more useful things as well. When you don't, we have ilmenite here and bam, that's all we want to know. We have ilmenite here, and maybe we do some sieving, and then we are finished. So what I try to say is to get more time into this characterization stuff. It definitely helps you in the end, and also definitely helps you to build up a processing scheme that is the best for this specific beneficiation plant, more or less this specific deposit. If there are no questions, I would thank you for your attention, and feel free to ask me. Otherwise, heartfully Glück auf.